So first of all, I'd like to thank you for the opportunity to be here. So I'm going to talk about semi-classical wave functions on the unit circle. I divide the presentation in 4 parts. In the introduction, I will recall some definition about orthogonal polynomials in the unit circle and some basic properties. In the second part, I'm going to talk about instruction relation, that is some finite relation that involves the polynomial and their derivative. In the third part, I will discuss about difference equations for the Verblunsky coefficients. And in the last part, I'm gonna give some examples on how to find the wave functions that satisfy these properties, this explicit structural relation and the difference equation. So the results of this talk can be found here in this article that has exactly the same name of this talk. And this is a work with Professor Cleonice and here my colleague Karina. So let's begin with the definition of orthogonal polynomials on the unit circle. So for us, phi n here means the sequence of monic orthogonal polynomials on the unit circle with respect to the measure mu. This means that we have this inner product, and when the polynomials has different degrees, this integral is 0. Otherwise, this integral is a positive number. It's well known that these monic orthogonal polynomials satisfy disaggregable recurrences. This means that the polynomial of degree n can be written as z that multiply the polynomial of degree n minus 1 minus this alpha here is the Verblunsky coefficients, and the multiply here the reverse polynomial. So the reverse polynomial of polynomial phi n is defined like this. So this part is well known, can be found in Siegel's book. So in this work, we are interested in orthogonal polynomials that are associated with semi-classical wave functions. So we are going to consider the measure like this. So here we have W, the wave functions, and W is a positive semi-classical wave functions if satisfy this first order difference equation, where here A and B are Luana polynomials. And also A vanishes at the singular points of the one divided by the measure W. This is a general definition that can be found, for example, here, Alfaro and Marcelin, and in Magnus. In general, the study of semi-classical wave functions is classified in terms of linear functionals, and these can be, this classification can be understood for us wave function like this. So we say that the wave function W belongs to the class PQ if here in the first order differential equation, A and B are polynomials, and the degree of the polynomial A is equal to P, and the degree here of this quantity that involves the polynomial A and B are equal to Q. So this definition can be found, for example, in Cachafeiro and Soares. This is the general definition of semi-classical in terms of the wave functions, and this is the general classification. We are interested in a particular case where the polynomials A and B are polynomials of degree at most 2 and can be written in this form. The coefficients of polynomial A will be A2, A1, A0, and the coefficients of polynomial B will be B2, B1, and B0. So our goal here is first establish instruction relation for the polynomial phi n. That is some finite formula that involves the polynomial and their derivative. Then we are looking for a difference equation for the Verblunsky coefficients that we will represent like alpha n. And we are looking also for all semi-classical positive wave functions that satisfy that Pearson-type equation, that is this differential equation of first order that I mentioned before. So we call this first order like Pearson-type equation. So in this work, we are restricting this in this case for A and B. Okay, so among the classification of all positive wave functions, we find an interesting example for that is like this one, W theta. We have here three parameters, eta, lambda, and beta. And this wave function generalize some wave function that is well known in the literature. For example, when the parameters eta and b is equal to 0, so we don't have this part, and also we don't have this part, we have just the sign. This is the wave function that produces the circular Jacob polynomials, can be found here, for example. When we take eta equal to 0, so we don't have this part, we just have this part, the sine and cosine. These produce the Jacobi polynomials on the unit circle. So I believe the first time that appeared was here, but this is a Rush paper, so it's also possible to find in English here. They also give this Jacob polynomial as example. And when the parameter beta here is equal to 0, so our wave function is just this part. These corresponding the polynomials that was considering in the work of Professor Sirihanga in 2010. So before I discuss the structure relation and the difference equation, I will fix some notation. So we are considered the monic orthogonal polynomials. So in the formulas that will appear later, we're gonna need these coefficients and also this coefficient. And here is the Verblunsky coefficient. This parameter here, gamma n, they satisfy this formula. This follows by the Zego recurrences, and when we use this, so gamma n in terms of gamma n minus 1 and the Verblunsky, we actually can write gamma n just in terms of the Verblunsky coefficient. This other coefficient, beta n here, is actually the derivative of phi n when we take z equal to 0. So we can write also, followed by Zego's recurrence in this formula, in terms of the Verblunsky polynomials and this coefficient gamma, but this coefficient gamma can be given in terms of the Verblunsky. So these both coefficient can be given in terms of the Verblunsky coefficient. Okay, so let's first, the first theorem is that when we have W, the wave functions, semi-classical that satisfy the first order differential equation that we call the Pearson-type equation, and the polynomials that appear in the Pearson equation are polynomials of degree at most 2. And if we have this addition condition, then the polynomials, if we multiply az by the first derivative of polynomial of degree n, this expression can be written as a combination of the polynomial of degree n minus 1, of the polynomial of degree n, of the polynomial of degree n minus 1, and here the reverse polynomial of phi n. And we obtain also these quantities here explicitly. So let's see this coefficient. So here is the structural relation. And the coefficient here is exactly this one, n times a2. The coefficient s and n can be written in this formula in terms of b1, e1, the coefficient gamma. So just to remember, phi and z is monic, so we have this, and the coefficient gamma is this one. So Sn, and in the two formulas that we find Sn, we appear this coefficient gamma. And the rest of the coefficients depend of the coefficients of the polynomial A and B here, and the Verblunsky polynomials. Okay, one interesting consequence of this instruction relation will be the difference equation. When we take this formula and we take z equal to 0, here, 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 and here, if we take z equal to 0, we found a discrete equation that I will mention in a few minutes. But first, let's take a look at the idea of this theorem. So just the idea of the proof. Here we have the polynomial that appears in the Pearson equation, the polynomial of degree 2. Here the first derivative of phi n. So the leader coefficient, if we multiply this one by this one, is this times this. And since we are considered monic orthogonal polynomials, so the leader coefficient of this one is n plus 1. And the leader coefficient of this one is a2 and z n plus 1, and so on. So this here is a polynomial of degree n, and the reverse polynomial. So we have here this expression has a degree at most n. Then we can write this expression as a combination of the orthogonal polynomials, phi 0, phi 1, into phi n minus 1, phi n. But we don't need everyone. If we use the orthogonality here, the orthogonality of the monic orthogonal polynomials, and also this relation here, this relation comes for the hypothesis of the wave function satisfy the Pearson-type equation. This relation here was first noted in the work of Magnus in 2013. And then using this orthogonality and this one, we actually, the coefficients of these terms vanished in, we just need the polynomials of degree n minus 1 and n. So this polynomial here of degree at most n can be written in this form. Then the rest is find the explicit value of the coefficient, these three coefficients. But the general idea is just using this two orthogonality property. Okay, so now the second part that we will discuss, the difference equation, follows exactly by this instruction relation when we take z equal to 0. Here, 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 and also here. And when we use the explicit value that I mentioned before of this coefficient. So this provides this difference equation for the Verblunsky, the sequence of Verblunsky polynomials. So here we have something that depend of the coefficients of the polynomial a and b, that multiply here the Verblunsky alpha n. Here also depend of the coefficients of polynomial a and b, that multiply alpha n minus 2. Here this part depend of the coefficients a1, a0, a2, the polynomial a, and also this gamma, and this gamma depends of all Verblunsky for j equal to 0 to n minus 1, that multiply this quantity here. So since the Verblunsky coefficients, we know that the absolute value, the Verblunsky coefficients is less than 1, so this quantity here is different from 0. Is everything okay? And in the formula of the instruction relation, we have two formulas for the coefficient s and n. We have two formulas. And using the two formulas, we can find actually two expressions for the difference equation. One of them is this one, and the other is in this form. So here we have the Verblunsky alpha n minus 2, alpha n minus 1, and here we have this term. And here also involve the Verblunsky polynomials. So because of these two expressions of S and n, we obtain two expressions for the difference equation. The motivation for this work comes from the modified Bessel polynomials. So here I'm going to talk about known results that can be found here and also in the book of Anas. So this wave function is well known to satisfy this instruction relation, where this quantity here can be expressed in terms of the Verblunsky polynomials. And the Verblunsky polynomials, since these wave functions is symmetric wave functions, they are real, and they also satisfy a discrete Pauli-Weyl of type 2, that is in this form. So this is well known, can be found here, and first appear here in Pearson in 1990. So let's take a look at the general discrete Pauli-Weyl equation. The general discrete Pauli-Weyl equation is in this form. Here, we can find here in the Van Ness book, for example. And our formula for theorem 2 that holds for also complex Verblunsky. They have some, it's kind of similar. We have here xn, here of n, xn2, here of alpha n minus 2, and we have this part xn minus 1 divided by 1 minus xn minus 1 to the power 2. So here we have the Verblunsky polynomials, alpha n minus 1 divided by 1, my absolute value of alpha n minus 1 squared. So they have some similarities. And just a few examples of Verblunsky coefficients are known explicitly. For example, the Bessel polynomials that I mentioned before, we know they satisfy the discrete Pauli-Weyl, but we don't have the explicit value of each Verblunsky polynomials. So here, now we are looking for the third part of this talk, that is which positive measures satisfy the Pearson-type equation where A and B are polynomials of degree at most 2 and satisfy the addition condition of the theorem 1. So we want to classify all possible wave functions. So the Pearson-type equation, we can rewrite them like this. So here we have the derivative with respect to theta, and here involves the coefficients of polynomials b, here b2, b1, b0, and the coefficients of polynomial a, here a2, a1, a0, a1, a2. So to find all possible choices for the positive wave functions, we define our analysis in 3 cases. The first case where AZ is a polynomial of degree 0. The second part, when AZ is a polynomial of degree 1. And finally, when AZ is a polynomial of degree 2. And then we are looking for all possibilities for the coefficients B2, B1, and B0 when we divide in these cases. So let's consider the first case where AZ, we are considered harmonic in all cases. So let's take a look at the idea for all possibilities of the wave function W when we choose AZ a polynomial of degree 0. So here in the formula, we have here A0 equal to 1, here 0, 0, 0, 0, and we have this. Where Z here is 8. So we want that our wave function be positive. So this part must be real. If this part is real, the imaginary part of this part must be 0. So when we impose this condition and we multiply these quantities, this equation here is equivalent to this one. So we take a look here, we have something that multiplies cosine of 2 eta, something that multiplies sine of 2 eta, sine eta, cosine eta, and here 1. But these functions are linear independent. So this means equal to 0, the imaginary part of B2 must be 0, real part of B2 must be 0, then the B2 must be 0. real imaginary part of B1 and imaginary part of B1 must be 0, so the coefficient B1 must be 0, and imaginary part of B0 must be 0, so here is 0, here must be 0, and here we just have a real number. Okay, then we have this, remain this, for we have a positive wave function that we can write like this in terms of derivative with respect to z instead of theta. So when we integrate with respect to z, the wave function must be like this. We have the exponential part. Here is just some constant positive. But our structure, for our structure relation, we also need this hypothesis. Since az doesn't vanish, so the value of the wave function at 0 and 2 pi must be equal. But when we impose this condition, equal to 0, the real part of B0 here must be 0. Then the wave function must be a constant. So we have actually the Lebesgue wave function. Now let's take a look what happens when we take a polynomial of degree 1. So let's consider the monic polynomial and written in this form. So using the Pearson-type equation, here A2 is equal to 0, A1 is equal to 1, A0 equal to R, and here 0, here 1, we obtain that the wave function W must satisfy this. So again, we are looking for positive wave function, so this part here must be real. And to analyze this, we multiply here by the conjugate, here z minus r prime. So here will be positive, and we need this numerator here. The imaginary part must be 0. Then we can find all possibilities for B2, B1, and B0. This identity provides a system of choices for B2, B1, and B0. So let's define the vector x here with the real part and imaginary part of B2, real part and imaginary part of B1, real and imaginary part of the coefficient B0. And we want to find all possibilities such that this whole. So this means that this vector x must satisfy this system. We have here a system with 5 equations and 6 unknowns. And our analysis must depend, the matrix here, F1 and D1, depend of the R. The R is here, the 0 of the polynomial A. So we need to divide our analysis. For example, when R is equal to 0, this part vanishes, this part vanishes. So these two lines of the system, we can don't add any condition. So that's why we need to divide our analysis. So the first analysis when R is equal to 0. Then we find the conditions for the coefficients B, and we find that BZ must be in this way. Then when we integrate and do all the steps that I made before for the polynomial of degree 0, we find this wave function. So this wave function appears in Marcella and Sirihanga in the context of current pair of wave functions of second kind. And notice when we take B2 here, the parameter that is a complex parameter like this, we actually obtain the wave functions associated to the modified Bessel polynomials that I mentioned. That was the motivation in the beginning. So the Verblunsky polynomials of the modified Bessel polynomials satisfy the point-Levé discrete of type 2. So just instead of using B2 and in B2, I define B2 like this parameter U to simplify our formulas. So the instruction relation from theorem 1 will be like this. Z, they multiply the first derivative of the polynomial phi n is a combination, a linear combination of polynomial of degree n minus 1 and and the reverse polynomial of phi n. And the discrete equation for the Verblunsky coefficients become this one. When we choose the parameter u equal to it divided by 2, this produces the wave function of the Bessel, the modified Bessel polynomials, and this discrete equation become exactly the discrete Painlevé 2 equation that I mentioned before. Now take a look for when the R is different from 0. So we have possibilities when R has absolute value equal to 1, n is different from 1. So we find this wave function. And when R is equal to 1, we find this possibility for the wave function. When the absolute value of R is different from 1, we obtain the Lebesgue wave function. So, okay, so let's take a look of this example here that has sine and exponential. I just recall the parameters here, lambda and eta, because this is the wave function that appeared in the work of Sirihanga in 2010. So for this wave function with this A and this B satisfy the Pearson-type equation, the instruction relation will be this in this form. So here is the AZ, they multiply the first derivative of phi n could be written as a combination of polynomial of degree n minus 1 and degree n. And the discrete equation for the Verblunsky become this in this form. So we depend here the alpha n minus 2 and alpha n minus 1. And here, just to recall this coefficient gamma n, we are looking for the considered monic polynomial. So this coefficient gamma n is this one. Okay, this is an example that these wave functions appear in the work of Sirihanga. So we know explicitly the monic orthogonal polynomials with respect to this measure in terms of the hypergeometric function, and the Verblunsky are explicitly. So this is an example where the Verblunsky coefficients are known explicitly. Also, using the classification of Cachafeiro and Soares, if W belongs to the class PQ, then also belongs to the class P plus 1, Q plus 1. So these wave functions belong to the class 1, 1. So then automatically will also belong to the class 2, 2. So when we are looking for the polynomials when we consider the polynomial A, polynomials of degree 2, this wave function will appear again because she belongs to the class 1, 1 and also to the class 2, 2. So now the idea is quite the same. So now we consider AZ a polynomial of degree 2, and we need to find all the conditions for the coefficients B2, B1, and B0, such that W be a positive wave function. So here we need to divide the analysis in more cases. So when R2 and R1 are equal, we have two equal zeros, and we need to define when the absolute value of these R is equal to 1 and different from 1. And when we have AZ has two different zeros, so we need to define when this condition means that the both zeros, R1 and R2, has absolute value equal to 1, and when the product of these two has absolute value equal to 1, but they are not, R1 has the absolute value different from 1. And when this product of these two zeros has absolute value different from 1. So we kind of need to dividing all these possibilities to find all hypotheses for the coefficient, all possibilities for the coefficients beta, coefficients B. Sorry. So I'm not gonna enter in all details, but we need to solve this system when we define the vector X in terms of the imaginary part of B0, real part of B0, and B1 and B2. And F2 is a matrix that depends of these R1 and R2, and D2 here depend also in R1 and R1 and R2. So let's focus on the example. That will be easy, but the idea follows the same. So this wave function that I mentioned before belongs to the class 1, and also belongs to the class 2. We just need to consider AZ in this form, Z minus 1, they multiply Z minus R, where R could be any complex number. And the coefficient B that appears in the Pearson-type equation will be a polynomial of degree 2, also depend here of this R. And the B here, that appear here, is this complex number that depends here on the parameter eta and lambda. So for each value of R here, we have different polynomials AZ and BZ, and we also retain different expression for the instruction relation and also different expression for the difference relation for the Verblunsky coefficients. So let's take a look at a few cases. When AZ is in this form, 0 is in 1 and then another 0 is 0. So this the derivative of phi n that multiply AZ can be written as combination of polynomial of degree n minus 1 and the reverse polynomial. When we choose AZ like this one, so this quantity can be written as combination of phi n minus 1, phi n minus 1, and the reverse polynomial of degree, the reverse polynomial of phi n. If we choose this one, we also need 4 terms. So here we need 3 terms, and for this case, the 2 cases, we need 4 terms. Phi n minus 1, phi n minus 1, and here phi n star. So this beta is just this number, this complex number, lambda plus e eta, where lambda is here and eta is here. So this is the instruction relation. Although if we choose another values for R, we produce another. The discrete, the difference equations, when we choose AZ like this one, become this, actually a linear difference equation. So although we already know by the works of Sirihang in 2010, if we don't know, by this formula, we can obtain the explicit value of alpha n. When you choose AZ like this one, the formula for the Verblunsky coefficients become this in terms of alpha n minus 2, and alpha n minus 1, and here involve the real part of gamma n. Just to remember, gamma n is the second coefficient here. And when we choose AZ like this one, we obtain quite similar here. We have plus, here we have minus. Here involve the real part, and here involve the imaginary part of this coefficient. And also alpha n minus 2, alpha n minus 1. Okay, so another example that appeared, that I mentioned in the introduction, when we multiply this is the wave function that I mentioned before. If we multiply by cosine, this is also a wave function that belongs to this class PQ, when P is less than 2 and Q is less than 2. So here, these wave functions satisfy the Pearson equation, where AZ like this one, and BZ is this one, polynomials of degree 2. If beta is different from 0, if we have this part, so these wave functions belong to the class 2. But when beta is equal to 0, then this part belongs to the class 1 as well. When we choose eta equal to 0, here we have a symmetric wave function. So we obtain actually the wave function of Jacob polynomials on the unit circle. And when beta is equal to 0, we obtain the previous example that belongs to the class 1 and 2. So the instruction relation for the monic orthogonal polynomials associated with these wave functions is in this form. depend of the polynomial of degree n minus 1, n minus 1, and the reverse polynomial. And we have here all the explicit value in terms of this d here, just to simplify the formula. So d depends the parameter lambda, beta, and eta that appear here, lambda, beta, and eta. And the difference equation become this one. So here d is this complex number. And when we take beta equal to 0, we recover the difference equation that I mentioned before. Also, when we choose eta equal to 0, then we have the wave function of Jacob polynomials on the unit circle. This is a symmetric function, and the Verblunsky are real. And then the imaginary part here will be 0. So if we consider this particular case, the instructional relation become this formula. So we have just the sine and cosine. And the difference equation simplified this in this form. This is another example that it is known explicitly, the Verblunsky polynomials and also the orthogonal polynomials. So for this case, the Jacob polynomials on the unit circle, the Verblunsky coefficients are real and are known explicitly. And the monic polynomial can be given in terms of the Jacob polynomials. So here the monic polynomial, Jacob polynomial. So these two are the polynomials, the Jacob polynomials on the unit circle, here with degree odd, here with degree even, and can be read in terms of the polynomials of the Jacob in this variable. So these formulas can be found here. Another example that appears for the case where A is a polynomial of degree 2 is this wave function, where U is a complex parameter and R must be a parameter that has absolute value different from 1 and also different from 0. So the polynomials A and B is polynomials of degree 2. These wave functions also belongs to the class T2 and appear here in the works of Marcelo and Sirihanga in the context of Sobolev orthogonal polynomials and current pair of measures. For this function, the instruction relation can be read in terms of 4 terms, polynomials of degree n minus 1, of degree n minus 1, and the reverse polynomial. And the difference equation for the Verblunsky become in this formula. Alpha n, here just depend the n and the parameters of the wave functions. Here R2, just depend the n and the 2 parameters of the wave function. Here we depend also the coefficient gamma, and here the Verblunsky alpha n minus 1. So basically what we have, the examples will be this one. For polynomials A of degree 1, we have these 2 families of wave functions. This first one, the polynomial B has degree 2, and the AZ has degree 1. In this second case, AZ has degree 1, and also BZ has degree 1. But also this example belongs to the class 1, 1, and 2, 2. So we can also find AZ like this formula and BZ basically this formula, polynomial of degree 2. These wave functions is interesting because generalize this one and this one. So this wave function appear here just for the case AZ and BZ has degree 2. This particular case, that is the Jacob polynomials on the unit circle, we need AZ be like this, so A and B polynomials of degree 2, and these another wave functions, also A and B are polynomials of degree 2. So here I have the references that we use, some of them. So here we have the definition of semi-classical orthogonal polynomial, but they mentioned there was Magnus, the first one that defined in the way that we are using. Here we have the classification of type. Here they look of type 2, but there's a general type PQ. Here is the work of Magnus that he defined these properties about semi-classical orthogonal polynomials with this definition in terms of the wave functions instead of functionals. Here, the book of Van Ast has a part of the difference equation that I mentioned about especially about the Bessel, modified Bessel polynomials. So thank you very much. And this was a work supported by CAPES and FAPESP.